begin. So a little bit about eDay Direct. We've been around since 1997, and this has been our journey, being the distributor, authorized distributor for Mentor Graphics for many of these years, and keep expanding with more products as Mentor become parts of Siemens. And this basically lists a quick, product overview of the software that we sell and support. So on the Mentor side, there are verification tools such as Questa and Visualizer, that what we'll be talking today. There are layout software as well as Valor for design and manufacturing. We have schematic integrity analysis, signal integrity analysis, and thermal analysis. Also, if you're designing products that need requirement and tracing, we do have a product from Siemens that's called Polarian. Jumping over on the Siemens side, we now offer the mechanical analysis tool, so that's MCAD, in addition to ECAD, with mechanical design tools, as well as analysis and structural analysis. Okay. In addition to the product, we also offer training and analysis service. So if you need training on any of the products that we sell, we can help you with those. And if you need some design analysis work on some of your projects that might be short of resource, we can help you with that. Please contact us for more information. Okay. So at this time, I like to switch over to Walter, and he will make a quick introduction as well as do the presentation. So Walter, go ahead.
As Kong said, today we're going to talk about the Visualizer Debug environment. You should be seeing the presentation now, right, Kong?
Yes, it's okay.
Okay, great. So I'm going to talk a little bit about Visualizer, what it is intended to do, how it is an evolution over the built-in debugger in Questa. I'll go into the design debug features, some of the system Verilog test bench debug features. That Visualizer setup section, I think I'm going to skip over, but Kong will have the slides available for you. So if you do get into it, you can look more in depth into that. And then I'll do a quick demo with whatever time we have left. So, we do these studies with Wilson Group once every few years, and we've seen this trend, and I think this is a little bit old slide. It's from 2014, but even if you looked at the newer data, I would say we see that engineers are probably spending now 40% of the time in the debug task. So, as much as people say we want a faster simulation, what we really find is it's that debug task where the most amount of your time is spent. So if we can do something to speed that up, that's going to be worthwhile. So the top challenges we see in the debug world these days are capacity. As designs are getting up into hundreds of millions of gates, we're really seeing that the original debugger for Questa, the tickle-based one, it's starting to, show its age, I guess, is the thing. So as these designs are getting bigger, we really feel like we need something that can handle that. Debug efficiency is just, we've tried to design Visualizer such that things that take you 10 or 12 clicks to do in the original debugger now maybe take you 1 or 2. And then test bench debug, in the system Verilog UVM world, that's where we've that's a whole new ball game. And so we've really taken to having a debugger that is targeted at that methodology. And then finally, we have a single debugger now that is for all of our tools, whether it's simulation, whether it's low power debug, or formal verification tools, or even maybe our emulators. By having a single unified debug platform, then you are not having to learn a new debugger for every one of your tasks. So all of our simulation, emulation, formal verification engines, they are all using Visualizer as a common front-end debugger. And all of our technologies, whether it's UVM, whether it's low-power UPF, whether it's RTL, or transaction-level debugging, it's all using the Visualizer front-end. So a little bit of a difference that you have to have versus using the original debugger is you need a couple of arguments in your VOP and your vsim commands in order to activate debug. So when you do your VOP command for optimizing your design, you want to get this -debug and then a design file name. Well, you want to do the -debug option and the -design file, which creates this design.bin, which is used by Visualizer. When you're doing your vsim, you tell vsim to now create, instead of the traditional vsim.wlf file, it now creates this qwave.db, which is a much more efficient way. So you say qwave.db and what signals you want to collect, and then between the two of those, that will generate all the files for Visualizer. So one of the things we see is it requires much less memory to collect the same wave data, and the simulations are much faster. So just as an example, one of the things that we're able to do is we no longer have to give that +ACC switch in the simulation environment. That kind of slows down simulation in order to collect this wave data. And, you know, on average, what we see is that if you are collecting the same amount of wave data, doing it with the traditional either WLF or FSDB style debug versus creating the QWave debug information, we'll see that we can simulate on average about 3 times faster or so. Depends on the design, but we see anywhere from 2 to 4x faster by not needing to collect all of that information with the +ACC switch. So that's one of the big advantages. And then once you are debugging on large designs, I don't know if any of you have ever been debugging in the traditional Questa debugger. When you have a really big design with a lot of wave data, you are like zoomed in and you zoom out full, and it takes like 30 seconds for the waves to slowly propagate across the window. Feels like about 10 minutes when you're actually doing it. That is indicative of the fact that that traditional tickle debugger is kind of hitting its capacity limit, whereas that's completely instantaneous within Visualizer. We have a few things, the time cone, I'll talk a little bit about the memory debug, which can really help tracing down certain bugs. And, you know, we've had customers tell us that it takes them 3 minutes to do it in Visualizer, whereas it took them 30 minutes to find something like that in the traditional debugger. And then again, when you get into the test bench schematics or the debugging UVM code, that's where I would say we really have some big advantages. A whole bunch of other stuff, multi-dimensional arrays, state machine, you know, when you're in the UVM world, when you're trying to browse certain instances of a class, there's just all kinds of stuff in Visualizer that helps out with that. So we really find that it's a very intuitive, natural layout. Navigation is easy. The windows are much more synced to each other. So as you click on different areas in the hierarchy, if I clicked on here, that would automatically bring up that source code. It would automatically, source code. It would automatically show all the variables for that. So some of this is in the other debugger, but like the syncing with the source code window is just way more intuitive in this debugger. Very responsive. As you navigating around in your design, as I say, the tracing back and forth is intuitive. When I click on this, you'll see this highlighting here. And what that highlights is based on where the cursor is dropped, this was the path that was taken through that RTL code at that instant in time. So you can get the execution trace, you get these pop-ups, things like that. I'll show you that more in the demo. And then when we get to the test bench, you can see all of your UVM test bench, what the hierarchy of that is, how it connects to the DUT. You can browse through there. You can look at all your object-oriented instances like classes and sequences, and all those things are available for debug, which I'll get into. So first we'll look a little bit at the design debug. As I said, all of these different windows are synced together. So as I click on the different places in the hierarchy, when I click on the packet buffer, it automatically shows the packet buffer source code. It automatically shows the schematic for that. You know, things are synced in a much more efficient way. I already kind of said that. Everything is synced with the wave window. You can search in the hierarchy, which I like this little search panel. Helps you find if you've got a really deep, complex hierarchy and you know you're looking for a particular instance, you can just do a search and it'll find that. So you can search on pretty much anything in your design, whether it's instance, design name, etc. You can do filtering there. As I said, one of the things that's really nice is finding drivers of a signal. So if you have a signal and you want to know where it comes from, you can just double click and it'll go to the driver of that. You can show all the drivers of a particular instance. You can map out a logic cone. Let's see. The signal clipboard is something for setting up your original wave window. You can bring up this signal clipboard, and then you get this hierarchy view here. You see all the variables. You can select things you want. You can move them over into this clipboard. You can rearrange that clipboard. You can go to some other instance, add some things from that. You can even add labels over here. You do all that, and you say go, and then that populates your wave window for you. So it's just setting up your initial wave window is really nice with that signal clipboard. As I said, the schematic viewer is just going to be, it's tied to whatever instance you're selecting in the design hierarchy. It will show that schematic viewer. It'll show that source code. There's some annotation to what's in this schematic viewer. So if you see here, these blocks are in red. Those are instances of lower level components. If you see a block in solid blue, that's a sequential logic block. If you see a block that's, you know, unfilled in color, that's a purely combinatorial block. I'll show you again more in the demo. You can add things to the wave window from whatever view. So if you select a signal here in the schematic viewer, you can right click and say add that to the wave. You can say show me the logic cone of just that signal. So it'll trace back and it'll eliminate everything else and just show you that logic cone. So here's that right here. I selected this signal. I said show me the logic cone. So it traces back to where that came from. Another thing that you can show is what's called the time cone view. And that's similar to a logic cone, but it adds sequential awareness to that tracing. So right here, I selected this signal and I said, show me the time cone for that. And so it's saying that this signal was produced at this time, and then it's tracing back, and you'll see this is a flip-flop. So now it's saying the input that generated that was at this time, and so you can see these time steps as you're tracing back, and that way it annotates the logic backwards sequentially in time so that you don't have to keep going and moving the cursor back one clock cycle to see what the values were here, and then moving it back again, moving it back again. So it just makes debugging those kind of things much easier. The finite state machine tracer, you can get things like a finite state machine table. You can see the source code. You'll see right here on this particular trace through, I traced through and I'm in the start read state, and then I can see what the next state is going to be. So these highlighted things are showing that. I can then, once I'm in there, I can step through the sequential state machine. I can add the state machine variables to the wave window. And again, I'll show that in the demo. Assertions. So we have a full assertion table and an assertion browser. This one is very similar to what you see in the traditional Tickle GUI. So we pretty much re-implemented that assertion viewer in this environment, and because it's in this environment, it's much faster, etc. Waveform viewer, very similar to any waveform viewer. You put things in the waveform. You can browse around. This kind of mimics the Verdi two-cursor mode. So you have a primary cursor and then you have a reference cursor so that you can get times between those. You can put things into an analog mode so that you can see, instead of a number, you can see that. If you have state machines, and especially if you're using kind of traditional Verilog coding style, where you have some parameters that you've set up and don't actually have an enumerated type, it will actually show that parameter name versus the numerical value of that state, which just helps in doing finite state machine decoding. You can do all the things that you normally would do, like modify radixes and put it in an analog view. You can add spacers and groups, and you can either split or concatenate buses, and then you save that format in the same way you do to a wave.2 file. As I said, it is pretty much a two-cursor mode. You use the right and left mouse button to move your primary cursor and your reference cursor, and you get the value between the difference between those cursors, or the frequency between those cursors is shown up here. You can step around through there. One of the things that I like is this thing we call biometric search. And so I can put in values. In this case, we just kind of said anything with a 7 in it. Let's highlight it in purple. That's maybe not the best thing to do. What I find this really useful for is if you have maybe an enumerated type and you want to see when a state machine goes into a certain value, you can put that enumerated value up here. Say every time it goes into there, it's going to be orange. And then when I'm zoomed all the way out in my wave window, I can kind of see, oh, there's an orange state. Let me zoom in on there because that's what I was looking for. Another thing that's useful is you can do things like if you're tracing sequences, maybe you're tracing a packet of data and there's a unique packet ID in there. You can put that packet ID in the enumerated search, and then you can see, you know, how that packet is flowing through your system. So a little more on biometric search. On the test bench debug side, you are now able to look at the whole test bench hierarchy after the initial enumeration of your test bench. You can see a schematic of that. You can see how it connects to your DUT. You can look at all the different classes. So you can grab a class, you can look at, you know, the main phase, the build phase, et cetera, in that class. Let's see. This is all synced up in the same way as the source code browser. So when I click on this agent config, it'll bring up that agent config code. It'll show me all the class instances of that agent. So I can go and I can grab a particular class instance and throw that into the wave window. You have a full class browser so that you can see things like, you know, what are all the tasks within my particular class. So this is the environment, and I'm showing everything in that environment. I can grab, you know, I can kind of see class instantiation, class hierarchy, all the different things about classes there. Those classes can be added to the wave window just like they were regular signals. So there's full debuggability of all your class agents in the wave window. You can do searches to find, you know, particular instances or particular, you know, how many instances of a particular class there are. And again, it's all synced to the wave window. Again, you know, if I click on that driver, I can see, you know, lots of information about that driver. I can browse a particular instance of that. I browse this, it brings up the information on that class. I can put that class into the wave window. If you use UVM macros, you know, in your source code, what you'll see is, you know, this UVM info, blah, blah, blah. And, you know, that can be kind of hard to know exactly what's going on in there. So we actually have this ability to click on a little plus sign there, and then that'll show you what that code for that macro is. And it just makes flowing through code that you don't know what's in that macro. It can be a lot easier to follow the code. So all of this information on the classes is available both in interactive debug, which is also available in that original Tickle GUI to some extent, but what Visualizer adds is full class debugging on a post-sim mode. So if you run a regression test, you still have full debuggability of all the class information in that post-simulation mode. So as I say, I can come down here, I can look at my test bench hierarchy, I can drive down to a particular browser, I can either browse that and see some information on it, or I can add it to the wave window. So that would add that class to the wave window. Once you add a class to the wave window, this is that driver, you can click on the little plus sign, and then that'll show you all the members and what's going on with everything within that class. So it really does facilitate debugging these classes quite easily. UVM sequences, similarly, if you have sequence objects, you can add those sequence objects to the class, to the wave window, and then, you know, again, everything within that sequence is available for debug. So for stream debugging, so if you have a stream of sequence objects, you can look at the sequencer and see, you know, what objects it created. So this was, you know, the target, where it was going, data. There's probably a unique identifier in here. And so you can drop those sequences into the wave window and see when the different sequence items existed and over what period of time they existed, and drill down into those. Similarly for transactions, you can drag and drop transactions into the wave window. Those transaction values you can highlight with different colors, and then we automatically do that for our verification IPs. Let's move forward on me. So all the verification IP is automatically, damn it, there's some timing in this slide. All the verification IP automatically highlights different transactions. You can manually highlight different colors for different transactions. So as I said, this visualizer setup section, I'm going to skip for now. I mean, we already talked a little bit about the two things you need to do. When you do your VOP, you do your design file and give it a design.name. By default, it's going to use design.bin. And then you say, you know, we need to debug this. And then when you run your simulation, you tell it to generate a Q-Wave DB versus a WLF DB. So for post-sim, you would do that. You would run your simulation, and then you'd bring up Visualizer. For a live sim, you would just basically give this dash Visualizer, and it would bring up Visualizer in live mode. So that's, I'm going to skip the down and dirty details on all that, and we'll give those slides to you. So basically, in summary, Visualizer is built for speed, both speed of the simulation to get you into debug mode as quickly as possible, and for speed of actually doing the debug. Because of the high capacity, there's no tool delays that you're waiting for, and because of the efficiency of the design, the debug tasks are much quicker and much easier to go through. So it really does increase your debug productivity. We're really good with very complex designs. We don't bog down due to capacity. We can handle, you know, native system Verilog or UVM debug environments, and Visualizer is built for all of our simulation, formal verification, emulation, system level testing. All of our different tools are progressing to Visualizer as the native debugger. So with that, I will bring up a demo. So I'm bringing up a Linux virtual machine. That is right now the one thing about Visualizer is it is only available on the Linux platform at this time. We are working towards bringing it to the Windows platform as well, but for the foreseeable future, next year or so, it's still only a Linux tool. So you can see here's a script to run a simulation and then bring up Visualizer. So the first, you know, part of it, the vlog, the compiles, that's exactly what you would do normally within Questa. And then right here, you know, when I do my VOP, I basically just said, let's go into debug mode and let's create a design.db file as my my database. What do see here, what you don't see here, is the plus APC switch. So we don't need to disable a bunch of the optimizations that VOP is capable of doing. And then on the VSIM side, we're going to run it in command line mode. We're going to run the whole test bench. And then I'd say -Q wave. And I'm taking all of my signals, any memory that's greater than 5,000 elements. I believe I'm 50,000 elements. Greater, less than, I'm not positive. 50,000 elements. Grabbing all of my messaging, grabbing all my transactions, grabbing all my classes, except I've got this filter.txt file, which contains all the base UVM classes. So I don't need to collect all that. I just need to collect all my custom classes. So this filter.txt says, let's grab all the classes except anything that's in this filter.txt. And I put in that filter.txt all the base classes. I'm grabbing assertions, I'm grabbing schematics, and then I'm just, running my simulation. And then finally, after my simulation is done, I call up Visualizer on the design.db and the QWave.db that got generated here. And so right here is that visualizer class. So you can see right here, I've got my my RTL code up right now. So this is the top of my RTL code. Here's my DUT, and you'll see as soon as I click DUT, my schematic view went to that. My source code view went straight to there. As I change that, both the source code and schematic changed. Now, if I zoom in here, I'll see, if I click on this blue block, it'll take me to that always block. It's blue, so it's a combinatorial block. It has a clock. It highlights all the source code for that combinatorial block. If I click on this one, it goes to that one. So I can quickly sync to everything there. So if I'm kind of tracing signals from here to where it goes, I can say, okay, I'm tracing it into here, or I'm tracing it to this block. This red block here, that's an instance of another block. So if I double click on that, it'll drop into that instance. Let's see. Let's look at maybe this guy right here. So this guy right here is a controller. If I click here, I can kind of see, this is case state. This looks like a state machine, which means as soon as I click that block, my finite state machine viewer is also highlighted. So if I click on this block, I got no finite state machine. This one I do. And then I can click different states within here, and it'll take me to that part of the source code. So let's go ahead and add to the wave all of those signals. Let's zoom into an interesting part of this. Let's kind of zoom in there just for now. Now let's close that for a second. Let's come back up here. And you'll see I can also add to the wave my finite state machine. So, let's select that. This directly from here, but maybe not. So let's go ahead and grab these signals. Okay, right here you can see that my state variable has a bunch of parameters that enumerate all these different states. And if I add all of these to the wave window, let me bring that wave window back up. How did I dock that? There it is. Pop it up. So you can see right here, this is my state variable. And that state variable is just a 10 down to 0 state vector, but it had all those parameters. And you see, if I zoom in, it's showing me the parameter name, not just the state value, which is way easier to follow than, you know, having to figure out what 000001752 means or whatever. So let's come back over here to Visualizer, and let's look at maybe, let's say I want to see every time I follow this memadd and then memaccess. So if I select that guy, you see now that goes to that source code. Let's go tools. Excuse me. Come over here to the wave window. Tools, biometric search. Let's add, and you'll see it automatically. If I was over here, cancel that for a second. This is that PMEM address. There we go. And let's come back over here and add. And I'm going to color code every time I see PMEM address, I'm going to make that blue. And every time I see this software mem access, I'm going to code that a different color. So let's come back over here, add another one. And let's color code that purple, pink. Okay. So now, if I zoom out a little, I just hit some. So add that state. Zoom out. So I'm zoomed out pretty far, and you know, like I said, I was interested in every time I went from that blue state to the purple state. So even without seeing the values here, I can, you know, oh, this is one of those areas that I'm interested in. So I can zoom into that, and then I can kind of come up here and see what other things were going on. So that's something kind of cool that the biometric search does for you. Let's see, what else? If I want to, I can bring up my UVM test bench hierarchy as well. So I've got my design hierarchy, and I got my UVM test bench hierarchy. And I can start, you know, going down through that, and you can see, well, first of all, if I go to my environment, view my UVM, where is that? Should have it somewhere. There it is. Okay. So here's my UVM schematic, and I can see, you know, what the hierarchy of my test bench is. That I've got several of these I2C agents that are connecting to my test bench. So there's different channels on this I2C that are sending data. Each one of those is also going back to a scoreboard. So I can kind of zoom out and I can see what that whole hierarchy of my test bench is. I can click on one of those and drop down to see just that one driver that I have a sequencer. That sequencer sends sequences to my driver, which then sends data to my DUT. You know, if I drill down further into these, you know, I can see both the source code for that I2C driver and the sequencer, etc. So I can do that kind of thing. Any one of these agents I can actually add that agent to the wave window. And then now you'll see that I added that I2C agent number 5. That's my I2C agent. And then the PIC instance of that, if I open that guy up, I can see all the elements of that. Let me zoom full and see. That's not necessarily a great. That guy isn't doing a lot. So let's see if there's something else in here that might be an interesting thing to look at. Let's look at my wishbone agent. Wishbone driver. So there we go. So my wishbone driver, I can kind of see that it's sending through several different addresses, different data that it's writing, and I can do my wave style debug on that. I can look at all the classes. So there's my different class agents. I can see the inheritance and stuff of the different classes. And I think that's probably what I'll do for today on this demo. If you guys have more questions, we can talk about that. You can put things in the chat window. But basically, going back to that last slide, Visualizer is our next generation debug environment. It increases your debug productivity. It handles large designs. It allows the simulator to run much faster. It allows your debug to be quicker. It supports system Verilog and UVM debug, and it's cross-platform debugger. So with that, I'm going to take a look at the chat window and see if there's any questions.
So normally, Walter, what would you recommend in terms of the machine hardware requirement for this? Right, this is pretty fast, and it's constructing logic on the fly, right, for getting the value. So would you say that there's not a hefty hardware requirement to run this?
I mean, the hardware requirement, the debugger itself is not going to be the thing. That visualizer is not going to be the limiting factor. It's probably your simulation machine is what's important. And, you might run your debugging on a local machine and, be running all of your regression tests on some big hardware machine. So I would say, oh, somebody just asked about the timecone viewer, and that's something that, I didn't go into. So anyway, I would say Visualizer is not going to be a thing that dictates your hardware. As long as you have a modern machine, you've got enough memory, you should be good there. So let me go back to this Visualizer demo and see if I can remember how to pull up the time zone here.
So while you're doing that, Walter, one thing to remember is that this is a post-sim. So as Walter mentioned, when you run the simulation, you set up your switches to generate these files that can be used by Visualizer later. So the advantage of that is that when you're in this debugging mode, you can traverse the whole waveform very quickly, versus in the original way when you take up a license for the simulator, then viewing window. So that's one huge advantage. But the methodology would have to be, done in a post-sim environment. Okay, you still can do the interactive if you like. Okay.
You can use this as an interactive simulator, so that while you're running your simulation, you can also be looking at the wave information. But the general use model for this is that most people are using it kind of in that interactive mode. So a little. So the time cone view, like here's a signal, and you know, and in this case, this signal is going undefined, but it could be that it just took on the wrong value. It could be a whole lot of different things that, you know, a whole lot of reasons that you would, you know, want to use this. But in this case, this signal took on an unknown value. So I'm going to go ahead and I'm going to say view. How do I do this? Oh, I think I click right here and view. No, that's the logic cone. So the logic cone, as I say, you can look at the logic cone and you can kind of trace back, but sometimes that's not real useful because you've got to keep changing the clock. So instead, I go through and I say view time cone. It should be here somewhere. View time cone.
Yeah, it's on the next one. Yeah.
Yeah. So let's top this off. Make this a little bigger. And so you'll see this is where I grabbed this signal. And I grabbed this signal at the moment it was transitioning from a 0 to an X. And so that was at this time 184,202 nanoseconds. And I'm debugging backwards. And you'll see these are all highlighted in red. So this signal is the same, is from the same clock cycle in all of these red areas. But then right here, you'll see, okay, at the time that this clock grabbed that and it went from a 0 to an X, the input to this register was an X because the output of this register just went from a 0 to an X. So, you know, everything over here is now highlighted from that previous clock cycle. And then that, again, comes here. Everything before that is from the previous clock cycle. And I can kind of keep going back. And, you know, if I click on this, if I go look at the source code now, I would see that that's just a buffer that's taken a whole bus. And so I've just got a single bit of that bus. And then, you know, right here, I finally get to where that's coming from. It's coming out of this memory. And this memory is putting out an X because the value that was read from this register, this value of F03, is currently an X. And you know, that keeps me from needing to go keep changing the cursor back to the, you know, input for each one of these registers. And so I can trace back to there. So I've traced far enough back. So now if I click on this memory, if I go back to my register, I can see here's the memory. And so that address, let's turn on the annotation. So that address is currently F03. So where did that address come from? I can go to that address, look at the address generator, and you know, one of the things that I'm noticing right here is, you know, depending on my operation, you know, I was saying, okay, use my base address plus 0, plus 1, plus 3, plus 3. So I think this is a mistake right here. I did add subtract, and then I did a copy paste error, and I didn't make this multiply. So this should have been H2. So that's you know, the kind of thing I can find by using that kind of cone view. Any other questions? So somebody said, how does Visualizer help speed up Questa simulations? And you know what that is that Visualizer, because we create that design database during the optimization phase, we still allow VOP to do a full optimization of your design. So we can do almost regression speed simulations, optimize away some internal signals that you know, normally if you were using the Pickle debugger, you would no longer be able to debug. But because we create this design.db file, Visualizer itself can basically back calculate anything that was optimized away. It knows why that was optimized away and what that signal was. And so we can do full optimization, get full speed debug, and then be able to trace back to anything that was optimized away for the simulation. So it allows basically probably 3-4 times